Okay, so last week we covered kind of intro to just descriptive statistics, and this week we are covering some basic rules of probability. So, let me see if I can pull up the slide that I think I put this. Okay, yeah, this is the one I want. Okay, so I think I showed this to you last week, and I said, so last week we covered descriptive statistics, and this week we're going to learn probability, okay? And the next couple weeks, actually this week and next week, we'll build off of probability rules and probability distributions, and then the central limit theorem. This is actually this week, next week, and the following week. So we're going to be learning about probability, and then we'll bring it together back with descriptive statistics as they culminate together in inferential statistics. So, do you guys remember what I said what inferential statistics was about, or kind of why we bother studying statistics? Okay, yes. So to find patterns or relationships in our data where we want to make conclusions about the world based on the data that we have. And the idea was we have a population that we cannot directly observe. Instead, we observe a sample. And based on what we see in our sample, we're hoping to make statements or conclusions about the population. Okay? And a lot of that depends on this question of, did what I see in my sample, the thing, whatever sample I observed, could it have happened just by coincidence? Could it have been just by random chance? Okay, that's essentially what a lot of our question is going to boil down to. And if the answer is it could have happened by random chance, or it is quite likely to have happened by random chance, then this sample does not really tell us anything about the population. However, if it turns out that it's very unlikely to have happened by random chance, then it tells us that our sample probably indicates something interesting in the population. Okay? And so to answer that question, could it have happened by random chance, requires us to understand some of the rules of probability. And so that's what we'll learn over the next, I'd say, 3 weeks. And then we bring that together with descriptive statistics. Okay, so let's get into Chapter 3 on probability. Okay, and so I'll just summarize I'll try to summarize what I just said, which is when performing So when performing inferential statistics, we often ask ourselves, could the data I see have resulted from random chance alone? If yes, it's open. Yes, I see your hand. Let me just finish writing this out. Okay, we had a question.
How do you determine if the data is p-guided by random chance?
Yes, so this is a very good question. We will answer that question, I would say, when we get to chapter 7 in our textbook, okay? And it comes from our understanding of probability, and we're going to look at how we can determine the probability of our data, okay? And so we have to get through kind of these sections on probability first, okay? Okay, so what I've written on the board says, could the data I see have resulted from random chance alone? I hope you can read my handwriting. And it says, if yes, then our data does not tell us much about the population. The data could merely be a result of chance, okay? So for example, someone might claim, I can predict the future, watch this, and they say, I'm going to flip a coin and it's going to land heads, and maybe they do it and it lands heads, and they say, haha, there you go, I've predicted the future. And then you say, well, do it again, and they say, no, this is just a one-time only thing. If they say something like that, you're probably not likely to believe them, okay? On the other hand, if they can do this repeatedly, after 10 times in a row, then you'd say, wow, maybe you can predict the future, or maybe you're cheating somehow, but I don't, your brain basically says, I don't think this could have happened just from random chance alone. Technically, it could have. There's a 1 in 1,024 chance of it happening by random chance alone, but probably you would say, well, something interesting is happening. And that's essentially what we're going after. So this requires that we understand probability. Oh dear, my screen. Okay. So I'll just write this. So a lot of times you see probability and statistics taught together. I would argue that they are actually two separate subjects. However, statistics applies a lot of our understanding of probability to draw conclusions from data. Okay, I'm going to move on to the next slide if that's okay. Okay, so we're going to just start off with some basic definitions of probability, okay? And so we might say we have some event, and we'll call it A, all right? And we say the probability that event A will happen is probability of A, written this way, okay? And the probability of any event must be between 0 and 1 inclusive, where if probability of A is equal to 1, then A is certain or always happens. And probability of A equals 0, then A is impossible or never happens. Okay. So we have some very basic notions of this already, and we'll say if I flip a coin, the probability that the coin lands heads is what? 0.5. So I know a lot of us are accustomed to saying things like 50-50, but we want to, I want us to get into the notion of saying numbers between 0 and 1. Okay, so we would say 0.5. You could say 50%. This is also acceptable. Okay, 50% also acceptable because that represents 0.5 essentially. But we would say the probability that the coin lands heads is 0.5, or we could write something like this. Or to simplify, we could just write probability of H. Something like that, okay? However, this, so we have this internal notion that the probability that a coin will land heads is 0.5, but have we ever stopped to think what exactly does it mean to say that the probability a coin lands heads is 0.5? Okay. Now, usually when I ask this question, somebody will say, well, the chance that the coin lands heads is 0.5, or the likelihood that it lands heads is 0.5, and we kind of list off synonyms for the word probability. But what does it mean to say the chance that a coin lands heads is 0.5? Or yeah,
the number of times on average.
The number of times on average. So what do you mean by that?
Like the more times you flip a coin, the more you see that the average of that number of coin tosses being heads is.
Okay, yes. So this is a very good interpretation, because you mentioned the idea of the more times we flip the coin, if we were to keep track of all of our results, we would probably see the coin landing heads about 0.5. Okay, so our notion of probability, we're going to take what's known as the frequentist notion of probability. Okay, so I'm going to just write that down here. Okay, this is, so let me just say, in this class we teach statistics in a classical view, okay? So, for example, I'm assuming some of you have taken physics, and when you took physics, you started off learning what they call Newtonian physics, right? You learn about like mass and acceleration and those types of things. And it turns out that that's great, but then I don't know if in your physics class you learned about general relativity, but it turns out that a lot of these rules of physics that we've learned from the Newtonian era is no longer applies when things approach the speed of light and things like that. And so the view of statistics and probability that we cover in this class is known as the frequentist view, and it's kind of our classical view of probability. Modern probability and statistics takes on what's known as a Bayesian view, I would say. The frequentist view still exists and is still frequently used. However, I think a lot of computerized things, probability models behind, Google's image recognition and things like that, those would be Bayesian views. But I would say that comes in future classes if you were to study this more. I don't know if you guys have heard that term Bayesian Statistics? Some of you maybe yes or no. Well, now that I've told you, you might hear it more, and I don't know, they'd like to throw it around as just tech speak for things, but so it's very interesting. We're taking a classical view, so we're going to learn tests kind of the classical way, and when we do statistics on the computer, we're also approaching them from a classical view, okay? And I think it's very important to learn the classical view first, okay? So I completely stand by our methods. However, as if you were to pursue, I guess, more advanced statistics or try to do statistics, people might ask for you to do things in a more, quote, modern approach. But the classical view is tried and true, and it's still very good. But I just need to throw that out there. Okay, so the frequentist view of probability, this we take on what's known as the long-run relative frequency. So we define probability as a long-run relative frequency. And the idea is, for example, maybe we can flip a coin 10 times, and maybe it lands heads 4 times. Okay, our relative frequency would then be 4 out of 10, or 0.4. You could get 5 out of 10 heads by chance. You could get 2 out of 10 or 8 out of 10. Really anything is possible. Some are more likely than others, but anything is possible, okay? As we flip a coin more times, so let's say we flip a coin 100 times, maybe we get 53 heads. Okay, so then our relative frequency would be 53 out of 100, or 0.53. Should I dim this first row of lights? Will that be helpful for you or no? We'll see. Better? Okay. Sometimes I have students sitting in the first row, and I don't think they like having the lights dimmed, but if this is better for the rest of the class, then here we go. Okay, and the idea is, as the number of flips approaches infinity, which is physically impossible, okay, our relative frequency approaches 0.5. Okay, and so this is the probability of the event. Yes?
So when defining the probability, like in this sense, say you have a six-sided die,
Mm-hmm.
It happens to be that the relative frequency was 53 over 100.
Okay.
That it landed on 2. So is the probability, would you say that it would be 0.53 also?
Yeah, so, okay, so this is, that's the exact next topic I was gonna mention, which is the difference between empirical probability and theoretic probability. And I think I'm hoping this will answer your question here, okay? Can I flip to the next slide, you guys? All right. Okay, so we've got empirical probability. Versus theoretic probability. Okay, and so empirical probability is the relative frequency we observe after performing either physical trials or simulations of the event. Okay, so if I physically flip a coin, 100 times, and it lands heads 53 times, then the empirical probability is equal to 0.53. Okay, and so if you roll a die or whatever you do, whatever you observe, that relative frequency you could call your empirical probability. Okay, and sometimes we create computer simulations, and we have, if we set them up properly, this could give us an idea of a probability. And sometimes so we'll learn some rules on, how to determine theoretic probabilities, and that's probably what the rest of this chapter focuses on. But sometimes things are too complicated to work out the mathematics behind a theoretical probability. So for example, maybe you're trying to understand the probability of someone developing cancer or something like that based on all of these other factors in their life. Okay? Well, if we wanted to create a mathematical model on how likely someone is to develop cancer, it might be very complicated to try to put things into formulas. Okay? However, we might be able to create a very good simulation. Okay? And if we can create a good simulation, we can simulate, 1 million people and just different, lifestyle things or things like that, and see what our simulation produces. And that could give us an idea of what the true probability is, even though it's based on a simulation and there's no, quote, math involved. Okay? And sometimes that's how we answer questions these days, because the math might be too complicated to answer directly. Is that... Okay, well anyway, that's what we do sometimes. So that's our empirical probability. Theoretic probability, on the other hand, is determined by the rules, or maybe I'll say mathematical rules of probability, if I can spell, or axioms. Okay, so for example, with the coin flip, we will say a coin has two sides. Each side is equally likely. Therefore, the probability that a coin lands heads is going to be 1 out of 2, or 0.5. Okay, so we'll probably spend the rest of today's class learning how to determine, learning these mathematical rules of theoretic probability. Okay. And what the law of large numbers states so the law of large numbers, or LLN, what this states is that as we increase the number of trials, yes, question?
What about the wind resistance against the line?
Oh, okay. So, well, let me address that in a second. Okay, as we increase the number of trials, the empirical probability we observe will approach theoretic probability. Okay, and so the question was, coin flip, what about the wind resistance of a coin? When you flip a coin, it's going to experience physics and all of these things. And, we get into this question of, is there really anything random in life? If somehow we knew exactly how much force was being applied to the coin, the speed of takeoff, how far the ground is from the coin, if we had a very good simulation, we might be able to correctly simulate exactly how many times we expect the coin to flip, and if we could model the properties of, we might be able to determine whether the coin would land heads or tails, okay? And people have actually done real studies on this, and it says, yeah, you can, for certain cases, you can actually simulate this and figure out whether it will land heads or tails, although for most intents and purposes, it acts like a random thing with 50% probability. The wind resistance can be factored in. It turns out it's rather negligible, and we is it truly 0.5? Could something happen? Could an eagle fly out of the sky and eat the coin mid-air? Technically, there is a non-zero probability of that happening, but a lot of times, the point of a probabilistic model is exactly to simulate some kind of real-life phenomenon in a kind of, quote, simplified fashion that captures the essence of what we're doing. So, yes, there are non-zero probabilities of other things happening to the coin, but for the purpose of simplicity, we say we're going to say 50% chance of heads, 50% chance of tails, and I'd say for almost all practical intents, this model is good enough. But just like when you learn physics, you learn force equals mass times an acceleration, and for most of your life, that is good enough until you're trying to reach things at the speed of light. Then that model falls apart. And so, when we talk about things of probability, we're essentially simplifying things down to simple mathematical rules. Does it apply in all cases? No. And that it's not trying to. You can always make your model more complicated. And the question is, whether you want to or not. Okay, so let's talk about some of these mathematical rules of probability. Okay. Yeah. Okay, so some rules. So we have, let's talk about event A, and we will have the event A has probability of A. Okay, so don't say that. So the probability associated with event A is assigned a number, okay? But don't assign the number to A itself. So it is not correct to say, it is wrong to say heads equals 0.5. This is wrong, okay? But it is correct to say probability of heads equals 0.5 because the event itself is not a number, okay? Or a I mean, it could be, but that's not the number that we're looking at. So we're always talking about the probability, and we're assigning a number to that, okay? We have something called the complement of A. Complement of an event. This is the event that A does not happen, okay? And we can write this a few ways. We can write it as A complement, or we can write it as A prime, or we can just write it as not A. These are all acceptable. And the probability of not A is equal to 1 minus the probability of A. So what is the complement of heads? Okay, if we flip a coin, what is the complement that the coin lands heads? Not heads, okay? So it is not necessarily tails, okay? The complement of the coin landing heads is not heads, okay? We might simplify, and we might say, in our simplified model of the world, not heads means tails, okay? But they're not exactly the same thing. Okay, so not heads, we can simplify and say not heads equals tails. And then we're essentially saying there's only two possibilities when you flip a coin. It either lands heads or it lands tails. Everything else is impossible, okay? We can do that. But they're not necessarily the same. So depending on your model of the world. So for example, yeah, maybe a more practical example would be what is the complement of being male? Complement would technically be not male. We might simplify the world and say not male means female, but you might be marginalizing a small but existing population in the world. So, just, these are just things to think about when you set things up. Okay. All right, we can calculate probabilities of more complicated events using a probability tree. Okay, so we have probability trees. Calculate complicated events. Okay, so there's in the book it talks about this slightly disgusting experiment where you've got a tank and I don't know, there's something in here and it's just filled with thousands of fruit flies. Okay, so this is just, lots of fruit flies living in this tank. And according to some rule, we somehow know that there are two types of fruit flies. we have gray ones, and we have black ones. Okay, there's gray flies and there's black flies. And the probability of selecting a gray fruit fly, I think, is 0.7. And there are only two types, so then the probability of selecting a black fruit fly would be what? Would be 0.3, okay? Because this would be probability of not gray. So 1 minus 0.7, 0.3. Okay, and you are going to, and there's thousands in here, okay? And so you are going to select 2 fruit flies. At random. And this is actually, this concept of selecting a fly at random is actually difficult to pull off in real life. And I'm not sure how we would pick a fruit fly at random on a practical level. Because it's not as easy as just reaching in there and grabbing one, okay? Why is just reaching in there and grabbing one not a random process?
You're still choosing which
Well, even if you had your eyes closed, why is reaching into a tank and grabbing a fly not a random process? Will it be biased in any way? Are you more likely to pick a certain type of fruit fly than another?
one. Any slower flies.
You're more likely to pick slower flies that, you know, for whatever reason, okay, right? Like, I don't know if I imagine flies know, like, I don't want to get squished by this selection thing. So you're more likely to select slower flies when you just reach into a thing and pick something. So, you know, with flies it's kind of gross, but, you know, if you had a cage full, not that a cage full of mice is any better, but if you just reach into a thing full of mice and you just grab one, you're more likely to pick a slower mouse, okay? And so, you know, if they say pick something at random, it's actually quite complicated. You probably have to number every single subject. So if it's mice, you have to number all of them, one through a certain thing. Use a random number device to select one of those numbers at random, and then pick those selected mice, okay? And with thousands of fruit flies, that's probably highly impractical, but we're going to just pretend we can somehow get random fruit flies, but let it be known, it's easy in textbooks to say at random, but in real life, it is a little bit more involved. Okay, so you're going to select 2 flies at random. Technically, when you select one fruit fly, it changes the proportion of the remaining fruit flies, right? Like if you select a black fruit fly, then technically there's slightly less than 0.3 black fruit flies in the cage. But we're going to say because there's so many, that change is negligible. Okay, so the change in probabilities is negligible just because there are thousands in this tank of fun, right? So, so we will ignore the effect of selecting a fly on the remaining probability. Okay, so then I'm going to ask, what is the probability that both flies I select are of the same color? Okay, and so to answer our question, we're going to create a probability tree. Okay, this node here represents the first fly that I select. Okay, And the first fly I select could be gray. It could be black. Do we spell gray with an E or an A in America? An A. I apologize. I've been spelling it the British way. Okay. All right. So it could be gray or black. And what is the probability that it is gray? 0.7. So I'm going to put 0.7 down this branch, and I'm going to put 0.3 down the branch for black. Okay. And again, now that I've selected the first fly, I'm going to select another one. So this represents my, this selection is the second fly, and that could be gray or black. The probability that it's gray again is 0.7, and the probability that the second fly I select is black is 0.3. If the first fruit fly is black, again, the second fly could be gray or black. And I would write 0.7 and 0.3, like so. Okay. Every time you have a node, all the branches coming off of that node, I could have a third one. You know, we could have gray flies, black flies, and red flies, or whatever. Whatever the probabilities associated with those, everything has to add up to 1. Okay, so the branches from a node must add up to 1. Okay. All right, and so to calculate the end results, okay, so what is the probability that I select gray then gray? That would be, I just multiply down the branches. I get 0.7 times 0.7, which equals 0.49. What is the probability that I select gray and then black? That would be 0.7 times 0.3, and I get 0.21. Okay, what happened here? If I go down this branch and then this branch, this represents what? Black and then gray, right? Which is distinct from gray and black, gray then black. So this becomes 0.3 times 0.7, 0.21, and lastly I have black then black, and I get 0.09. Is everyone satisfied with this? Okay, and then if I were to add all of these up, these also all add up to 1.0, showing that this exhausts all possibilities. Right? That there's nothing else that could happen because the probability of all 4 events combined is 1, meaning that it is always going to happen that one of these 4 things will happen. Okay, and so the original question was, what is the probability that both flies I select are of the same color? How do we answer that? So are of the same color, what results qualify for this? Gray, gray, black, black. Okay, so we're going to take 0.49, 0.09, and so our answer here, the probability is equal to 0.49 plus 0.09, 0.58. How are we feeling about this? I saw some faces of, so if anyone has any questions, I'm happy to try to address them. If there's any questions as to where I'm getting any of my numbers, or yes?
I'm actually confused about the 0.7.
I'm sorry?
We got the PR grade.
Probability grade, I just made this up. Okay, this is just made up as part of the problem. I'm just saying somehow in this tank of flies, 70% of them are gray. Okay? Which we can do that conveniently when we're making up problems, but okay. Is that feeling all right? Let's try an example here, and I'm gonna introduce a few concepts here. We have something called conditional probability. Okay. And so we might have events A and B. Okay. And perhaps once maybe these events have an influence on each other. Okay. So, for example, maybe we have one question we ask, do you consider yourself politically liberal? Okay. Okay, and so the answer we'll just say yes or no. We'll say those are the only two possible answers. Okay, do you consider yourself politically liberal? Yes or no. Okay, and so we'll say, and if they answer yes, then that means we'll say liberal. So A means somebody said yes to the question liberal. Okay, and then B, we will ask, are you registered as a Democrat? Okay, and the answer there also will be yes or no. Okay, and so B will be, if they answered yes, so B will be Democrat. Okay. So these, we can see that the answers to these questions are going to be very much connected to each other, but they are not the same question, okay? Because you might have people who consider themselves politically liberal, but not registered as a Democrat. And you might have people who don't consider themselves politically liberal, but may be registered as a Democrat, okay? But probably by and large, if they answer yes to the question, do you consider yourself politically liberal? Probably, I assume a majority will say, yes, I am registered as a Democrat, okay? At least in the United States. Okay, and so, I don't know where we're doing this survey, but let's say the probability that someone answers yes to the question, I am politically liberal, is, I don't know, what do you think is a reasonable number here? Depending on where. I guess the answer is like where we're asking, but let's just say across the United States, so we'll say 0.37. I don't know. Okay, and maybe that's, no, I guess it's all how we define ourselves, what liberal means or not, okay? And then we'll ask, so then over here, I'm only going to have what we have, conditional probabilities, okay? And so we'll say probability of Democrat given liberal, okay? So there's a vertical bar here, and we read this as the probability that someone is a Democrat or is registered Democrat given, essentially meaning if we know that this person is liberal. Okay. So what is a likely number for this thing? Probability of Democrat. What is the probability that someone is a Democrat if we know they answered yes to the question, are you liberal? This will be something like 75, yeah. So someone said 0.9, someone says 0.75. We'll just say like 82. All right, I'm just making up a number. Okay, so this says if they answered liberal, then they're registered Democrat. 82% of them are. Okay, so maybe some of them just aren't registered for a political party or something. I have no idea. Okay. And so over here, then we might also want to say, well, if someone, okay, so here's a good question. What is the probability that someone is not Democrat, given this person answered yes to the question liberal? Okay. Can we answer this, or do we need more information?
18.
Yeah, so the answer is 0.18, right? Because if we know that you have answered yes to the question liberal, then either you have answered yes or no to are you registered as a Democrat, okay? There's no other possibilities here. You either, if you've answered yes to the question liberal, then the next thing is you've either registered Democrat or you have not. So these are the only two possibilities here, okay? So this is necessarily then 1 minus probability of Democrat given liberal, and I'm just abbreviating there. I just want to make sure this is okay with everybody. Okay, over here then, if someone is not liberal, what is the probability that they are a Democrat? Okay, and so just so as you distinguish, again, this is just, I've made up this number, and this number is one that we're going to have to make up also. So if someone is not says I am not liberal, what is the probability that he or she is registered as a Democrat? Just throw out a number that seems fairly reasonable.
0.16?
Okay, sure. So we'll say 16% of those, when you surveyed, are you liberal? They said no. And then you said, well, are you registered as a Democrat? And we'll say, of the people who said no, 16% of them said, yes, I am registered as a Democrat. Okay? That sounds reasonable. I have no idea. Okay? I mean, we're just making up numbers here. Okay, so we'll take these numbers here, and these are the three relevant ones. Probability that someone is politically liberal to begin with, probability that someone who is liberal is a Democrat, and someone who is not liberal is still a Democrat. Okay, so again, this is then the probability that someone who is not liberal is registered as a Democrat. Okay. Yay? So far so good? Okay, so then let's turn this into a probability tree. Okay? Alright, so we can then use this to ask a question like, what percentage of people are registered as Democrats. Okay, and I don't know this answer, and I hope the numbers we selected are reasonable enough to get us a number in the ballpark figure, but if these answers come wildly off, don't hold it against me here. So what we're going to do is we're going to start off by saying, because of the information that we have, we're going to take this piece of information. So I'm assuming you have these written in your notes somewhere, right? So we're going to say, okay, so someone can either be liberal or not liberal. And then if they consider themselves liberal, they may then be registered as a Democrat or not. Okay. So what is the number I should put right here? Probability that someone is liberal. 0.37. So I'm going to put this number here, and I'm also going to label it with the symbol probability liberal. Okay. My notation is a tiny bit sloppy in that probability. So this is, you don't have to write this, but I might say probability liberal, and I might also just write P liberal. And in the texts, you know, our textbook consistently uses PR, but other textbooks just use P, and so I'm also a little bit sloppy in that regard as well, and I hope that doesn't throw anybody off. Whether you include the R in there or not, the truth is it doesn't really matter. We know what you're talking about, okay? Okay, and so over here, probability not liberal would then be what? 0.63, right? And so this would be probability, I'm going to write not liberal, okay? All right, if the person we selected is liberal, then what goes down this branch for ending up Democrat? 0.82, and so I'm going to write that this is then probability of Democrat given liberal. And that means right here I would have 0.18, which is probability of not D given liberal. Okay, so then fill out the rest of the table and answer this question. What percentage of people are registered as Democrats? I'll, if you're watching online, I'm going to pause the video right here, and I'm going to give everybody a minute here to fill out the rest of the table and then answer this question. What percentage of people are registered as Democrats? Okay, so based on the previous slide, this essentially is, if we know the person we selected is not liberal, what's the probability that this person is a Democrat? So this is going to be probability of Democrat given not liberal, okay? And so the number we put there is going to be 0.16, which means over here, because everything has to add up to 1, this must be 0.84, and this is going to be probability of not Democrat given not liberal. Is that okay with everybody? Okay. All right, and then so to answer a question, what percentage of people are registered as Democrats? Okay. There are two ways someone could be registered as a Democrat. Okay. There are those who are liberal and registered as Democrat. There are also those who don't consider themselves liberal, but are also registered as a Democrat. Okay, so those two paths are this one and then this one. And so the probability of going down this path is going to be 0.56 0.37 times 0.82, and I can multiply that out and I get 0.3034. And over here I have 0.63 times 0.16. And I have 0.1008. Is that okay? Okay, and so if I wanted to write these out completely, okay, this is effectively probability that someone is liberal and Democrat. Is that okay? Probability that someone is liberal and Democrat. And what numbers did I multiply to get that? I did 0.37 times 0.82. 0.37, if I want to represent this symbolically, what do I say? This is probability of liberal times probability of, what do I fill in here if I want to do this symbolically? I did 0.37 times 0.82, so what does 0.82 represent? This thing? Democrat given liberal, okay? There's an important distinction, right? Democrat given liberal. So the probability that I just randomly select someone and this person happens to be liberal and a Democrat is the probability that we first select someone who's liberal, and then beyond that, that person then has to then be registered as a Democrat. Okay, so that would be Democrat given liberal. Okay, so please understand the distinction between liberal and Democrat versus Democrat given liberal. Is it okay? So to get this, we do this times this. So here I'm getting 0.37 times 0.82, and this number is 0.3034. You good? I hope. Okay, I've got some head nods and smiles, so that's a good sign. Okay, and I always like smiles. It's like my anagram of my name. So we have 0.3034 and 0.1008. So to add these together would give us the total probability that someone is registered as a Democrat. And I have 0.4042, which I think is reasonable as far as the percentage of people who are registered as Democrats. Is this okay? All right, so let's, I'm going to continue on here. I'm going to actually copy this slide over. And put this up here. And then I'm going to ask another question. Okay. If someone is, so actually let me cut this top text out because we won't be using this. So if someone, what I want to ask is, if someone is registered as a Democrat, what is the probability this person is liberal? So symbolically here, we want to ask, what is the probability of what? What is the piece of information that we do know? What is given to us? That they're a Democrat, right? So we're going to have our vertical bar, and the part that goes after the vertical bar is the part that's given to us. So I'm going to write Democrat right here. And what I want to know is, what is the probability that this person is liberal? So I've got liberal, vertical bar, given, Democrat. How do you think we should answer this question? Okay. Well, if I select someone at random, what's the probability that this person is registered as a Democrat? Point 0.4042, right? We just answered that on the previous page. We said the probability that someone, if we select at random, the probability this person is a Democrat is 0.4042. We got that by combining the two groups of Democrats. There are liberals who are registered as Democrat, and there are non-liberals who are registered as a Democrat. Okay? So effectively, once that you have been given this piece of information that someone is a Democrat, we are now limiting ourselves to just this branch and this branch. Okay? Now that I've told you, now that I've given this, we know that there's no possibility of us being in this group or this group, right? Okay, so effectively, we've limited ourselves to just those who are Democrats. So in our denominator, I'm going to put in 0.4042. Okay, and I want to know, okay, now that I know that someone is a Democrat, I want to know what's the probability that they went down this top branch, okay? Because there's two ways somebody could have ended up a Democrat. They could have gone up the top branch or down this lower branch here. And I want to know what's the probability that they are Democrat by going up the top branch, meaning they actually are liberal and not liberal. Okay. So I want to know what's the probability that someone is liberal and Democrat. Okay, and notice I'm using the word and not a given there. So of the 0.4042 who are Democrats, how many are liberals and Democrat? This number, right? 0.3034. So I can now answer this by doing 0.3034 divided by 0.4042, and I get 0.7506. So according to this data, or this probability tree, if someone is registered as a Democrat, what's the probability this person is liberal? The answer is 75%. Okay. And maybe that is or isn't reasonable, but this is what our probability tree tells us. Again, we made up all of our numbers, so I have no idea if this is a good approximation of reality or not. But that's what we have. Are there any questions? So maybe I'll give you guys an example, and you can just try to make sure, we'll make sure we understand. Yes?
I guess I'm a little bit confused with the second branch.
Uh-huh.
Because in the second branch, we already know that those Democrats were not liberal.
Yes, that's
So
correct.
I guess I'm not understanding why we still have to factor them in our...
Because because they are still Democrats, right? So I've told you I've selected a person, and the only thing we know about this person is that this person is registered as a Democrat, okay? So we don't know if this person is liberal or not. And so we want to know, okay, this person is registered as a Democrat. Is this person liberal? Yes or no? And that's what we want to know. So we have to include the possibility that they're a Democrat who's not liberal. And that's why we have to include the second branch in there. Okay? Anything else? All right, so I'm gonna give you another example, and I hope we can answer this. Okay. Yes. All right, so this is a slightly funny example. Just the situation is hard for me to imagine in real life, but oh no, I guess it's okay. All right. Okay, so suppose that 1,000 women took a pregnancy test. Okay? And among the 1,000 women, 1,000 women, only 80 of them are actually pregnant. Okay. We have a pregnancy test. We'll say this is a low quality one. Okay. Okay. So the properties of the pregnancy test. Okay. So if a woman is pregnant, is actually pregnant, the test reads positive. We will say 98% of the time. Okay. But if a woman is not pregnant, it still reads positive. 1% of the time. Okay. So a high quality test shouldn't have this 1%, but I'm saying we, huh? It should not be 2. These are different different things. So okay, so then I'm going to ask you to make a probability tree. Okay, and we're going to ask what percentage hang on, let me just make sure let me change this top number here. I apologize. We'll say 100 of them, okay? Okay, so make a probability tree. I'm going to say, what percentage of women will test positive for pregnancy? Is that even how you say it? Okay, and then I'm going to ask another question. If a woman in this group tests positive, what is the probability she is actually pregnant? Okay, so I'm going to pause the video here if you're following along online. So take a moment and pause the video yourself, and we'll give you guys a chance to solve this question. Okay, I realize some of you are still working, but for the interest of time, let's go over our answer here. Okay, so I'm going to set up our tree such that we can either select a woman who is pregnant or not pregnant, okay? And so the probability of someone being pregnant selected is going to be 100 out of 1,000 or 0.1, okay? So this is probability that a randomly selected woman is pregnant, which means the probability that a woman is not pregnant will be 0.9. Once we have a woman who is pregnant, she could test positive or negative. And so the probability of testing positive, given that she is pregnant, is going to be 0.98. So this is going to be probability of positive given pregnancy. And over here, we're going to have probability of testing negative given pregnancy, or basically it has to add up to 1, so I'm going to have 0.02 over here. Same down here, positive and negative. If the woman is not pregnant, it still reads positive 1% of the time, 0.01. Okay? And this will then give me 0.99 on the bottom. Okay? So just be careful. You know, as I was walking around, I saw people writing 1% as 0.1. Just don't mix up your decimals and percentages. Okay? So 1% is 0.01. It'll throw off your answer by a lot. Okay, and so if we multiply down the tracks, we'll get 0.098, and this is equal to the probability of pregnant and positive. Okay, and then the other way someone can test positive is multiplying down this track, 0.009, and this is the probability of not pregnant and positive, okay? Giving a total, if I add these two up, I'll have 0.098 plus 0.009, and that will add up to 0.107. So what percent of women will test positive for pregnancy? 10.7% of women. If a woman in this group tests positive, what is the probability she is actually pregnant? Okay, and so in this case, 0.107 of the women test positive, and of those, only 0.098 are actually pregnant. And so to answer this question, we have to do 0.098 divided by 0.107, and we find that only about 92% of the women who test positive are actually pregnant. Okay, so that would be an indicator of a low-quality pregnancy test. It shouldn't do this. Okay. Yes. Question.
You didn't use the previous percentage.
I did. Or what do you mean?
The 0.107.
That shows up in my denominator.
Actually, sorry, I meant, how come you use what percentage are actually pregnant? The 0.1?
0.1?
Yeah.
Okay, because it is because the test is not perfect, the percentage of women who test positive is not the same as the percentage of women who are actually pregnant. And that's why there's validity to this question. If this test was perfect, then if a woman tests positive, what's the probability she's actually pregnant? If it was a perfect test, that answer would be 100%. If you test positive, 100% you're pregnant, okay? But because it's not a perfect test, and in fact this is a rather low quality test, she's tested positive, but she's not necessarily pregnant, and that's why we have to use the probability of testing positive in the denominator, and then the probability of actually being pregnant and testing positive in the numerator. Okay. Is that distinction clear?
Yes.
Okay. And there's also this small group of women who are pregnant. She took the test, and the test said negative, but she'll be in for a surprise, right? So that could happen too. Pregnancy tests, modern pregnancy tests are much more accurate, but over-the-counter ones at least. But the only ones that are close to 100% accurate would be blood tests if you go to the doctor and things like that. So anyway, let's take a short break here. We'll say 10 minutes.